Hello everyone, welcome you all to this new video. So till now I have covered 5 videos of this module and all of the topics which is there in your syllabus. I've tried to cover all of them till now. So there are some more topics to be conducted in the upcoming videos. I'm going to do it and let's quickly wind up with module 1. So around again some 4 to 5 videos are left and module 1 would be completed. So only few topics are left. One by one, let us cover all of them. I'm not doing multiple topics in one video and making the video lengthy. Why? Because it would be getting bored for you guys as well. Okay, so that's why if I do the lengthy video for this subject where I'm not doing any calculation stuffs and all, just putting these notes in front of you guys and just explaining, so that's why it would be very boring. So that's why I've tried to be making the videos in under 15 minutes. Okay, if I extend the video and make it around 20 to 25 minutes, in around 4 to 5 videos I could be completing one single module. But that is waste of use for you guys as well, because you won't be liking to watch the lengthy videos, right? So that's why I'll keep the videos as short and as possible and make more extended videos, more multiple videos. Okay, so that's why I'm making around 10 videos for each modules, because all the topics are very important. You cannot be skipping any one of them. So that's why which and all are important, which I feel in with my experience, because I've already studied this subject right in my third sem. So based on that, only the important ones I'm trying to cover it, okay, which is there in your syllabus. So with that intention only I'm doing these videos. So yeah, those who are new to this video, please like this video, subscribe to our channel. So let us continue with the concept. Till now we have discussed many concepts with respect to the voltage divider biasing circuits, some other kind of biasing circuits, uh, q point analysis, what do you mean by biasing, two supply emitter bias circuits, VDB amplifier, and how the amplification is getting affected with respect to some parameters. We have discussed it, along with many example problems of steps to calculate the VDB analysis circuits. Everything we have discussed so far, right? So now all these things we have discussed, we are going to be channelizing them in the space here. Okay, that is the free space with respect to the small signal operation. Okay, so with respect to that, all the things we have studied till now, that we are going to be channelizing in in the upcoming videos or upcoming concepts, whatever we are going to be studying. Okay, so before that, you should be knowing what do you mean by this small signal operation here. Okay, so you see here, this is one signal distortion graph which is mentioned here. Here the signals are getting distorted here. Okay, this is the plot of vi characteristic plot of IE versus VBE, and these are the different q points which we generate for different values of currents and voltages. And with respect to that, we are getting this plot here. Okay, so with respect to these three q points here, we are getting the sinusoidal waveform, and the signal distortion is happening in this case with respect to the variation in this values of IE and VBE, in order to get this kind of plot for the cube point, right? So how this is obtained, let us see that, and how the signal distortion would be affecting this circuit and affecting this operation. Everything we are going to be seeing this year. Okay, so just note this figure down, very important. If they ask to give an example for signal distortion with respect to the variation in the values of IE and VBE and the Q point, this graph you could be simply noting down. Okay, and let us see how this is getting obtained. So you see here, when an AC voltage is coupled into the base of the transistor, an AC voltage appears across the base emitter diode. This produces the sinusoidal variation in the VBE as shown in the figure 9.10. So this is the sinusoidal variation which we get with respect to these Q points. So when the voltage increases to its positive peak, the instantaneous operating points moves from Q to the upper point. You see here, they are mentioned clearly that the voltage is getting increased here. Okay, so that's why when the voltage here it is increasing like this, and when voltage increases, we know that these two are inversely proportional to each other. So that's why the current would be also slightly increasing, okay, with respect to the resistance. So that's why we are getting the q point getting shifted from one point to other in this way in order to get this plot here. Okay, so when the voltage increases to its positive peak, the instantaneous operating point moves from q to the upper point here. Okay, that is, this is the operating point q, and when it's getting increased, the it is going towards this upper point. So on the other hand, When the sine wave decreases, that is this is the Q point. Here it is getting increased from this point, and here when it gets decreased to its negative peak, the operating points moves from Q to the lower point. Okay, so that's why here when it is getting decreased, it is coming to this point, that is the lower point. So with respect to these parameters, the signal distortion we would be obtaining. Why? Because with respect to the values of the voltage VBE and IE, we would be getting the upper and lower Q points. So based on that, we are getting one signals which are getting placed in this pattern here. So this is the main reason for the distortion. Okay, so here how this distortion is getting established and how can we reduce this. Okay, so that's why here they have mentioned distortion and reducing distortion. What do you mean by this? You see here, the AC emitter current is not a perfect replica of the AC base voltage. Since the graph is curved upward, the positive half cycle of the AC emitter current is stretched and the negative half cycle of this negative half cycle is compressed. Okay, so this stretching and compressing is called as distortion. Okay, so for the positive half cycle, the amplitude here you could see it is getting stretched here. It is getting the amplitude for this negative positive half cycle is very high compared to this of the negative half cycle. Okay, so that's why in this case it is getting stretched, and in this case it is getting compressed. Okay, so that's why the stretching and compressing of signal with respect to the variation in the voltage values under VI characteristic plot, that is called as signal distortion. Okay, because we in the positive as well as the negative half cycle, you see here we are having the variation in the amplitude part. Okay, in this here also, in this part it is not visible in the naked eye, but there is the signal distortion happening here as well. Okay, so in the positive and negative half cycle, the we could be seeing in the variation in amplitude, so that's why it is called as signals are getting distorted. Okay, so this is meant by distortion. So how to reduce this distortion is they have mentioned it here. So one way to reduce this distortion is by keeping the AC base voltage small. Okay, they have mentioned the solution for this, that is you should be keeping the base AC voltage slightly smaller as compared to other parameters of voltage with respect to the transistor terminals. Okay, so AC base voltage you keep smaller than the emitter and the collector voltages. So when you reduce the peak value of the base voltage, you reduce the movement of the instantaneous operating point. Okay, so when we reduce the AC base voltage, so this is the fixed operating point, right? So if we reduce the value of AC base voltage, so we won't be getting the uh, more we won't be getting the upper point and lower point this far here. Okay, somehow nearer we would be getting the point. So if we get the point Q point, upper and lower point very near to that of the Q point, you the distortion chances would be getting very less, and somehow the for the positive and negative half cycle the amplitude variation would be slightly equal. Okay, so that's why this is the one solution they have obtained here. You should be reducing the AC base voltage. When you reduce the peak value, the base voltage, you could be reducing the movement of the instantaneous operating point using 10% rule to minimize the distortion. The peak and AC value of this emitter current IE must be small compared to the IEQ. Okay, so that's why this is the relation. This is not required, where IE is the AC emitter current and IEQ is the DC emitter current. Okay, so this is the relation they have obtained, that is IE is equal to point is less than zero point 0.1 IEQ. Okay, if we obtain this relation, there are minimal chances of signal distortion which is getting taking place here. Okay, so this is all about the small signal operation. Okay, with respect to the VI characteristic plot and the movement of Q point, we are getting the signals obtaining here, and these signals are varying with amplitude in positive and negative half cycles. So that results in the signal distortion. And one way to reduce this distortion is by keeping the AC base voltage small. What happens if we keep this AC base voltage small? It would be reducing the distance between the Q point, that is upper point and lower point. It would be coming slightly nearer to the Q point. So if the upper point and lower point are nearer to that of Q point, we would be getting that there are less chances of getting signal distortion. And in the positive and negative half cycle, nearly the amplitude would be getting equal. Okay, so you should be reducing the AC base voltage. Along with this relation, you should be keeping in mind, that is IE, that is the AC emitter current, is less than or equal to zero point 0.1 IEQ, capital IEQ. Okay, so that is called as DC emitter current. Okay, so this is all about small signal operation, and this is with respect to AC beta. So with respect to the beta component, so this is not required. So this is the AC resistance of the emitter diode. So this is important. Okay. So before concluding this video, let us discuss this concept, that is AC resistance of the emitter diode. Okay, that is also called as RE dash. Okay, this is very important because we are using this component RE dash as one constant value in multiple circuits or multiple problems where we are going to be seeing in the upcoming videos. Okay, so that's why I thought to do this AC resistance of the emitter diode. Okay, so here you see here there is one simple VI characteristic plot with one fixed Q point, upper point and lower point. So based on that we are so this they have kept it by reducing the base voltage. Okay, well, you see here if you compare this plot with this main plot here, here the points are slightly nearer to each other, so that's why you could be seeing that it is somehow in a straight line. Okay, so if it is in a straight line there are less chances of distortion. So that's why here the base current they have reduced it, and there is no distortion in this graph here as mentioned here. Okay, the positive and negative half cycle, the amplitudes are nearly same, and there is no distortion in this circuit happening. Okay, so now we see here when a small AC voltage VBE change at the emitter, the base junction produces the AC emitter current as shown in this figure. Okay, the AC emitter resistance of the emitter diode is the AC base emitter voltage divided by the AC emitter current, that is Re dash. AC resistance of emitter diode Re dash is equal to VBE divided by IE. Okay, both are small letters. The small letter indicates that it is in AC mode. Okay, keep that in mind. The capital letters indicate that it is in DC mode. All the components, resistor, voltage, current, whenever you see the small letter R, small letter V, small letter I, simply you should be keeping one thing in mind, that is in the AC mode. Okay, so that's why it is AC resistance, AC voltage and AC current. So that's why all these things are in small letter, and this is the equation for AC resistance. Re dash is equal to VBE divided by IE. The AC emitter resistance is also 25 millivolt divided by the DC emitter current. So this 25 millivolt is there, right? That is one constant fixed value which we need to be using for VBE. Okay, that is 25 millivolt. In case of DC, we are having the capital VBE as zero point 0.7 volt. You remember, right? Whereas for AC emitter voltage, this is that constant value you need to be remembering, that is 25 millivolts. So we can conclude it by saying that the AC resistance equation is equal to Re dash is equal to 25 millivolt divided by the DC emitter current IE. Okay, so this is the equation you need to be knowing. Re dash is equal to 25 millivolt by IE. Okay, keep this in mind. This we are going to use in the upcoming videos as well. Okay, yeah. So that's all for this video, guys. In this video, we have discussed with the small signal operation, signal distortion, how it is getting taking place in the signal with respect to the Q point shift, upper point and lower point, and how to reduce this distortion. Also, one solution we have found out, we should be reducing the AC voltage. Based on that, the Q point, so the upper point and lower point would be coming nearer to the Q point. With respect to that, we would be getting all the Q points in the straight line. And if you mark it here, and we would be getting the signals, the sinusoidal signals, in such a way that in the positive and negative half cycles the amplitude would be nearly equal to each other, which would be resulting in no signal distortion. Okay, so that is one thing we have discussed. Along with that, we have discussed with the AC resistance of the emitter diode, that is Re dash is equal to 25 millivolt divided by IE. Okay, so these concepts are very important. Again, once again, you see this video if you have not understand it. So that's all for this video, guys. In the next video, we are going to be discussing with one more important concept related to the transistor models. Okay, so let us see that in the next video. That's all, guys. Thank you. Like this video, subscribe to our channel, keep supporting us. Thank you.